So for our final talk of this session, we have Andrew Brown. Andrew is both an engineer at Intel, and he is also on the technical steering committee of the Bytecode Alliance. And in this context, he's also a PhD student, so wearing a lot of different hats. So take it away, Andrew.
All right. Let me get my clock. 20 minutes, right? All right, cool. Good morning. My name is Andrew. I'm here with Andrew Tolmach in the back, trying to present a talk on meta tracing for WebAssembly. So our approach is to build a set of distinct tools that will use trace-based optimization to improve interpreter performance in WebAssembly. And we're interested in feedback on whether our tools are useful elsewhere or specific details of our design. Okay, can I get this a little higher? Is that better? Good. So we start from the following scenario. Developers write programs in a high-level interpreted language, and the interpreter is compiled to WebAssembly. Then we have many users which invoke each program many times, and for each invocation, the input is dynamic. You might see the 0, the 1, the 2, the 7, but we know that the program and interpreter pair is static. And WebAssembly hosts like function as a service or distributed compute hosts of various kinds will run these invocations in a WebAssembly engine. And the problem is that interpreting these programs is slow in an interpreter compiled to WebAssembly. And so we're attempting to solve this with our design. And one thing to note is that this particular scenario enables us to do things offline because there's multiple invocations of the program. So we'll argue that this problem matters because there are already various attempts to solve this. So there's the just-in-time compiler approach, and for our scenario, this would look like finding hot functions with while an interpreter is executing. Compiling the program's bytecode to WebAssembly, and then somehow patching that new WebAssembly into a running WebAssembly instance somehow. So Dimitri from Megalia has demonstrated this approach last year at WASM.io, and this is a very natural, common sense approach, but not all interpreters have a JIT. The WebAssembly spec has no standard way to patch JIT compiled code into an instance. And as Chris kind of mentioned earlier, this approach is too risky for some hosts. And so that led to a second approach, which is the partial evaluation approach that Chris described earlier. Briefly, kind of 3/4 through the talk, he talked about Weevil. And so in our scenario, to describe his approach, a tool would combine the interpreter and the program bytecode, both which are static, to specialize the interpreter for that program using partial evaluation. And Chris and Max built Weevil to do just this for interpreters that are compiled to WebAssembly. So this is a well-studied approach, been taken by Graal and Truffle previously, but it is complex. It does require minimal source code changes to the interpreter, which we're trying to avoid. And it's naturally limited to the information that you have statically. So you know the program bytecode, the interpreter code. That's all you know at the time. And so our approach is distinct in a few ways. So our direction is trace-based optimization. And so specifically, the approach we're taking here is called meta tracing. And I'll explain that in more detail later. But the general idea is we collect traces of WebAssembly programs, and then we create optimized fragments from those traces, from the hot regions within those traces, and then we insert these optimized fragments into a new optimized program, and then we run that optimized program later. Our reasons for choosing this approach is that no JIT is needed, and so all kinds of interpreters can benefit from this approach. We can build distinct reusable tools for each phase in our infrastructure, and those might be useful elsewhere. And we kind of believe these offline WebAssembly to WebAssembly transformations are simpler and perhaps faster because when you do this stuff online, you have to make up for the runtime overhead of tracing and optimizing as the program is executing. We don't have to do that in our offline scenario. So the big question for us is, will the trace-based approach that we're trying improve interpreter speed? And I just want to point out that there's a history of trace-based optimization, but just the differences with our approach is that we should be able to take any user language as our trace, for tracing, and that we're doing this offline instead of online. So let me walk through an example to describe how meta tracing might work. So what we have here is a Java program that on the right has been compiled to Java bytecode. Now, of course, one might want to compile Java directly to WebAssembly, but for our research prototype, we're not doing that. We're just going to keep this bytecode separate. And so you'll notice that this Java program has a loop, and we'll call this loop the user loop. So the body of this user loop, that's the bytecode on the right. And then the Java interpreter, we're going to interpret this bytecode. That's written in C, and it has a loop which we'll call the dispatch loop. And so this retrieves the bytecode and implements the bytecode. And so 2 observations here. Most of the execution time is spent in this user loop or due to this user loop. And secondly, when we're interpreting this Java bytecode, everything related to the dispatch loop has overhead. And so what does meta tracing do to improve this? Well, let's just focus in on 3 of the opcodes inside that loop, the load, the add, and the store. And I sort of split out the interpreter part of this into a control flow graph, kind of simplified. And so if we trace our execution, the execution of these opcodes, you'll see that we spend some time doing dispatch stuff. Then we do the user load. Not all the instructions are shown for brevity, but then we come back to the top of the dispatch loop, and we do that again, and we do that again. And you'll see in green that that's the user loop parts of this. And what meta tracing does is it finds those and it extracts those things into an optimized fragment, getting rid of the dispatch loop overhead. So 2 intuitions here. One, if we can avoid that dispatch overhead for the user loops, we can improve performance, right? But we need to assume that the bytecode is not changing under our feet. And secondly, once we get the implementation into this optimized fragment, an optimizer can do a better job, or there's more optimizations available to improve performance. But what do we do about this asterisk? Guards for off-trace exits. What about, for example, this opcode, compare greater than or equals to? You can see the implementation in C for that opcode. And in our trace, we'll get events that look like this. We'll get an event that is related directly to the dispatch loop, which is operating on the bytecode itself. But then we'll also get events that are related to the actual implementation of the opcode. For example, if we're greater than or equals to whatever number, we need to do this versus that. So if a guard fails, so we need to maintain this logic. This unknown control flow needs to be retained in our optimized fragment so that our optimized fragment is still correct. And we do that by the means of guards. So our optimized fragment will include guards that if the guard fails during the execution of the fragment, we have what we call an off-trace exit. So we're leaving the assumed path of the hot loop, and we must de-optimize to the original interpreter. Typically, how that's been done in the past is we reset all the original interpreter state and we go to that location in the original interpreter. But even though that's a known problem for meta tracing and kind of solved, how do we do that in WebAssembly? There is no go-to in WebAssembly. The structured control paradigm of WebAssembly prevents that. And so I've given you sort of a broad overview of what meta tracing is, what the problems are going to be, and now let me dive into our design, and I'll dive specifically into two topics here, finding loops and how we're going to de-optimize these off-trace exits. And so, a general overview of our architecture is that first we will instrument the WebAssembly program, which is an interpreter, to capture traces, one or more traces. Then offline, we'll use that trace to find loops and optimize the loops into these optimized fragments and somehow reinsert them back into the, this WebAssembly program. And so then subsequent invocations of the interpreter will use this optimized version, which has been specialized to the program. And when we get to an off-trace exit, we'll de-optimize somehow. So we'll talk about that later. And the green check marks here mean that we have working prototypes for some of the phases. Our primary data structure in that design is the trace. And so that's a list of events that can recreate an execution. A trace could be saved to a file, but size and collecting the trace, those are limiting factors here. So our current approach is to just instrument a WebAssembly file with WebAssembly host calls. And this is naive, and we know it'll slow down execution, but we know that there are future mitigations that may resolve this, like reducing the number of events or using special hardware. I won't talk about that here. Our main goal for these traces is to use them to do meta tracing. So, find those user loops and make those optimized fragments. But there are other things that the trace could be useful for, like creating macro ops or for branch hints, which we can talk about later. So let me dive, more deep into how we're going to find these user loops. So what you see here on the left is a trace, and the trace events describe what happens, what are the branch decisions at these BR table instructions. What we then do is we apply an algorithm, a string algorithm taken from DNA sequencing analysis to find tandem repeats. So these are repeated subsequences within a trace. So, but when we get those tandem repeats, is this truly a user loop? So you'll notice that the values for this instruction, 29, 27, 162, those are byte
Yeah. So I was wondering when you mentioned like finding the PC, that technique seemed like it was specific to a WebAssembly interpreter interpreting another interpreter, which is a Java interpreter in this example, which is then interpreting a user loop. I mean, is there a way of, I don't know, phrasing this in a way which doesn't imply that the function that you're optimizing, because, I mean, originally we're talking about like arbitrary functions where you know the function, but it's not, that function might not be an interpreter. Is there a way of phrasing this which, you know, isn't so tied to being interpreter specifically?
Yes, I think it could be. So specifically, you know, it's important that we have a specific use case to target, and it's known that interpreters can be improved via meta tracing. So we need to at least hit that. But I'm hopeful that tracing would be able to find other opportunities that are not specifically interpretation, where the same kind of pattern happens, right? Like the data has a specific, you know, essentially a user loop that a trace can extract, and then we can generate an optimized fragment for.
Hi. So is this approach like tailor-made for specific interpreters? How difficult would it be to use it for a new kind of interpreter for a different language, something like that?
So the idea is you compile your interpreter to WebAssembly. So as long as you can compile your interpreter to WebAssembly, then the next decision is if we can automatically find the PC, good, perfect, no work needed, right? You just have to compile the WebAssembly. If we can't find the program counter automatically, then we may need to ask the interpreter author to add an annotation, say, hey, here's our PC. But that should be it.
I'm not sure if I understood it fully, but the block lifting translation you showed looked a bit like a CPS translation. Is that?
Yes, that's correct. It is
right?
Very similar. Yeah, go ahead.
So that might suggest that stack switching could be another alternative.
True. Yeah, I've looked into that a bit. I still have to fit all the pieces together, whether that is in fact the case. We had hoped to use stack switching perhaps as a ancillary, you know, to help with that switch. But yeah, I'd be interested to talk more to see what you think.
I mean, it'd be interesting to see what the performance cost would be as well.
Yeah, that's a big unknown here.
Yeah.
So.
When you were looking at kind of existing previous works, did you find any people who'd already experimented with partial evaluation for WASM in different ways, or are you kind of the blank slate here?
Well, we're kind of doing the trace space approach versus partial evaluation. Chris already has the partial evaluation locked down, so. But I've not heard of anyone else doing tracing in WebAssembly specifically.
Okay, thank you. Let's thank Andrew one last time.
Thank you.